Okay, here's example 2, where we are given only the initial concentration of our weak acid, and we have to use that to find the hydronium concentration and the pH. So hydrocyanic acid is HCN, and when this reacts with water, we produce the cyanide ion and hydronium. It's balanced at a 1:1:1 ratio, so we can sub it into our ice table. Ignoring liquid water, the only piece of information I have is the initial concentration of HCN, and I can assume that initially I have 0 cyanide or 0 hydronium. So we're looking for the hydronium ion concentration at the end. I don't know how much it's going to change by, so I can assume that it's going to increase by X moles per liter. These are a 1:1 ratio, so the cyanide will also increase by X moles per liter. So at equilibrium, I'll have X for each of my products. The hydrocyanic acid, because it's a 1:1 ratio, will decrease by the same amount as the products are increasing by. So at equilibrium, we'll have 0.500 minus X for hydrogen cyanide. Again, the way that it is now, if I were to set this up in my Ka expression, Ka equals products over reactants, I'm going to end up having to use the quadratic formula to solve for X. But luckily, with the rule of 1,000s, we may be able to get rid of this X here. So to check the rule of 1,000s, we take the concentration of our acid and divide it by Ka. If it's bigger than 1,000, then we can ignore this change here. So I've got 0.500, and the Ka value for hydrocyanic acid, if we look for it on here, (6.2) times 10 to the minus 10 is the Ka value. So we can sub that in. 6.0 times 10 to the minus 10. And we get a really huge number. We end up with 8.1 times 10 to the 7, which is way bigger than 1,000. So the rule of 1,000 applies here, which means that we can ignore the change in concentration of our weak acid. So the change is very minimal. Initial concentration equals concentration at equilibrium. The Ka value for hydrocyanic acid is 6.0 times 10 to the minus 10. Substitute in products, which is X times X. So we can write that as X squared over reactants, 0.500. So when we set this up to solve, we'll start by multiplying both sides by 0.500 to cancel here, which will give us 3.0 times 10 to the minus 10 equals X squared. Take the square root. And we get X equals 1.7 times 10 to the minus 5. So this is my hydronium ion concentration at equilibrium. It's 1.7 times 10 to the minus 5 moles per liter. If I take negative log of that answer, then that will give me the pH as well. So negative log of 1.7 times 10 to the minus 5 gives me a pH of 4.76.